In theory, decentralized AI looks like this visualization: a frictionless, sovereign application layer where intelligence flows freely across a perfect, trustless network. Peel back the software layer of Web3 AI protocols, and you find Amazon, Google, and Microsoft hardware. These centralized providers enforce terms of service, comply with government orders, and occasionally go down. When they fail or face censorship, the disruption bleeds straight upward. The math is unavoidable. If your compute layer is centralized, your AI layer inherits every single centralized point of failure. The protocol might be permissionless, but the physical hardware underneath is entirely permissioned. In late 2022, a specific architectural category was defined to solve this exact dependency: DePIN, or Decentralized Physical Infrastructure Networks. DePIN attempts to be the mandatory physical layer that makes true decentralized AI possible. The sector currently holds a $9 billion market cap. To determine if that valuation is justified, we have to rigorously audit its operational reality against its technical promises. To separate viable sovereign infrastructure from standard blockchain marketing, we must define strict architectural parameters. This triad model demonstrates the first requirement: a three-sided platform. You need distinct hardware suppliers, a coordinating protocol, and paying customers. Traditional Bitcoin mining fails this test. The miners don't bridge the gap to a customer base. The miners themselves are the service. The second axiom requires token-based supply incentives. If a network does not reward infrastructure providers with tokens to solve the cold start problem, it is simply a standard hosting company. The third axiom requires tangible asset deployment. The network must coordinate actual hardware, like this physical processor, in real locations. Pure software protocols do not qualify. If a project fails any of these three conditions, it is not sovereign infrastructure. It is a traditional business with a token attached. Once a network meets these axioms, we categorize its architecture by a single metric: spatial dependency. Does the physical location of the hardware actually matter? Digital resource networks, or DRNs, provide fungible resources. In a DRN, it makes zero difference where the physical machine sits geographically. Global GPU compute networks and decentralized storage and distributed bandwidth operate here. Conversely, physical resource networks, or PRNs, deploy hardware where specific geographic coordinates are mandatory. Look at these transmission lines. Energy grids, localized sensor networks, and autonomous vehicles require hardware physically bolted to exact locations. PRNs are building the framework for a future machine economy. But for decentralized AI to survive today, its immediate operational dependency relies entirely on the location-agnostic DRN compute layer. This is the baseline for enterprise compute: pristine, highly standardized rows inside a centralized data center. It is highly reliable, and it is highly expensive. Against this standard, DePIN compute networks offer a massive cost advantage. GPU access on these decentralized protocols is typically priced $45 to $60, and debugging failures across a globally distributed, trustless network introduces severe engineering friction. For high-stakes production workloads, that initial 60% price discount is rapidly consumed by required over-provisioning and continuous engineering overhead. This illustrates the DePIN flywheel. Tokens attract hardware supply, which attracts enterprise demand, generating fees to support the token's value. But right now, this engine fails. The mechanism stalls here. Converting token-subsidized hardware into paying customers is the hardest problem. Consider the compute protocol, io.net. At their peak, they claimed an impressive supply of 327,000 GPUs on their network. Yet the verifiable reality was drastically different. Only roughly 6,700 of those GPUs were actually active and processing organic workloads. Look at this massive hardware scale. Across the sector, vast walls of subsidized capacity sit completely idle, waiting for enterprise workloads that don't exist yet. The distance between reported supply and verified demand is the defining feature of this market. The sector's $9 billion valuation is currently a synthetic metric, driven by subsidized supply, masking a profound lack of paying customers. This matrix maps subsector readiness. Top right, compute is mature. Render and Akash process real workloads with verifiable revenue. Top left, bandwidth operates at scale, but providers earn pennies. Bottom right, confidential compute emerges for enterprise privacy. Bottom left, machine economy builds identity for future autonomous devices. As we see, true decentralization is a fractured landscape. Builders have to selectively integrate only the mature components while waiting for the rest of the ecosystem to catch up. When we revisit the architectural stack, the operational goal becomes clear. The vulnerable, centralized bedrock is removed, and heavy, interlocking DePIN protocols slide into place, creating a solid, sovereign layer beneath the application. The unvarnished reality is that DePIN remains an early-stage, imperfect sector, plagued by severe demand imbalances and high operational friction. But despite its flaws, it serves as the strict physical validator for any project. It dictates whether a protocol's claims of digital freedom actually hold weight in the physical world. A project can execute a flawless token distribution and perfectly decentralized governance, but if all of its compute runs on 3 AWS instances, the entire system is hollow. DePIN is the mandatory bridge. It is the physical layer that transforms decentralized AI from a theoretical white paper into unstoppable infrastructure, operating entirely beyond the control of any single entity.